Okay, the last type of applications we're going to look at are science-based. It's exponential growth and decay. Again, let's define some of the variables that we have. Q is the quantity. That's the amount after our exponential growth and decay. Q sub 0, anytime you see a subscript of 0, that means our initial amount or our amount before any growth or decay. Lowercase r is our rate. It's called a growth rate for exponential growth, and it's called a decay rate for exponential decay. That makes perfect sense. And then t is our time. So we have an exponential growth and decay equation. You can see that those equations are almost identical to each other. The only difference is in the exponential decay equation, you'll see that our exponent is negative rate times time. Okay, so let's just jump right into an example. A certain type of bacterium increases its population from 100 to 300 in 5 hours. What is the growth rate? Well, what information do we have? We know that our initial amount, Q sub 0, is equal to 100. The quantity that we have, Q, after the growth is 300. And we know that our time is 5 hours. So these don't need to be in years or anything like that. This is a different application than we had with annuities and simple and compound interest. Very similar equations, but we can have any amount of time. So our growth rate, we'll substitute everything into our equation since this is exponential growth. So we have 300 is equal to 100 times e raised to the r times 5. And you can see that this is the same equation that we had for a is equal to pe raised to the rt power, which is continuous compounding. Let me erase that. That's the same equation, just different variables. Okay, divide both sides by 100. So 3 is equal to e to the 5r power. Again, we're going to take the natural log of both sides. So we end up with the natural log of 3 is equal to 5r because the natural log of e is 1. And then we're going to divide both sides by 5. So we have r is equal to 0.2197. So about a 22% growth rate. So part B, how many bacterium will be there in 10 hours? So now our time is 10. So we're trying to find our quantity at time 10. So that's going to equal 100 times e raised to that rate that we just found, the one that's 0.2197 times 10. So if we solve this side, we end up with 900. So we start off with 100. In 10 hours, we end up with 900 of those bacterium, so they grow pretty fast. We're going to skip the next example, so we can do that in class. And let's take a look at radioactive decay. So radioactive decay, we have a variable h that is going to represent our half-life for our substance per some unit of time. And then the nominal rate of decay per this unit of time is given by this equation. R is equal to the natural log of 2 over h, then the time of our half-life. So we have radioactive radium. It has a half-life of 1,620 years. What is our nominal rate of decay? Well, that's R is going to equal the natural log of 2 over 1,620. So if we calculate that, that's 4.28 times 10 to the negative fourth. Part B, how much of 25 grams is left after 1,000 years? Well, that's Q of 1,000. That's what we're trying to find, is equal to our initial amount of 25 grams times E raised to the negative power, because we're decaying, so we have to do the negative of our rate, which we just calculated. And that's being multiplied by 1,000 because that's our time in years. So if we calculate that out, we get 25 times 0.6519 approximately equal to 16.3 grams. So if we have 25 grams after 1,000 years, we should end up with 16.3 grams.